In our everyday world, distance guarantees isolation. If you break a solid object in half and move the pieces far apart, they cannot affect each other without a physical connection or a traveling signal. Now let's shrink to the subatomic scale to look at two identical particles born from the exact same event, flying in opposite directions. Under classical physics, these particles go their own ways. What happens to one has zero effect on the other. But at the scale of photons and electrons, Sir Isaac Newton's rules break down. The submicroscopic world does not obey our everyday logic. These tiny particles have a property called spin, a type of angular momentum. Before we actually measure them, they don't have a definite up or down spin. They exist in superposition, meaning they are spinning both up and down simultaneously. So what happens if we leave these two connected particles in this undecided state and separate them by the width of a galaxy? The answer to that question requires us to abandon our foundational understanding of physical space. If we measure the particle here on Earth and find it has an upspin, the particle in the Andromeda Galaxy instantly snaps into a downspin. The coordination happens in zero time. This information coordinates across millions of light years, absolutely instantaneously, exceeding the speed of light. Albert Einstein struggled with this observation. His theory of relativity rested on the law that no signal can travel faster than light. He famously mocked the idea of such an instantaneous link, calling it spooky action at a distance. To save the logic of relativity, physicists proposed an alternative. Think of it like ordering a hamburger and a hot dog in identical boxes. If you open your box and see a burger, you instantly know your friend has the hot dog. This suggested the particles secretly possessed definite opposite spins from the moment of their birth. This sparked a fierce debate among the greatest minds of the 20th century. Einstein argued for hidden variables that dictated the outcome, while others insisted the particles remained undecided until the exact moment of measurement. The stakes were massive. If Einstein was wrong, the universe was not the predictable local place physicists had assumed it to be for centuries. Decades of rigorous testing finally provided the answer. Einstein's classical fast food theory was incorrect. In their undecided, vibrating state, no invisible signal or physical force bridges the dark vacuum between them. Instead, the math describes a collapse of the wave function. The singular act of measuring one particle forces the entire system to decided states simultaneously. Physically and mathematically, these are not two separate objects communicating with each other. They operate as one single, unified system. In the quantum world, physical space between entangled objects is simply irrelevant to their shared existence. This physics is no longer confined to thought experiments. Scientists are currently harnessing entanglement in modern laboratories. By entangling atomic systems, researchers are building clocks so precise they would not gain or lose a single second in 33 billion years. Adding more atoms into these entangled networks increases that precision linearly. We are also using entangled photons for quantum cryptography. If an intruder attempts to tamper with the network, observation immediately alters the quantum state, making the intrusion obvious to anyone monitoring the system. These emerging technologies move entanglement out of theory and into hardware, showing that our macroscopic experience of distance is an approximation of a much more complex reality. To see the true scale of this, we have to zoom out to the scale of the entire cosmos. Nearly 14 billion years ago, absolutely all matter in the universe was compressed together into one infinitely dense point before the Big Bang. If every particle in existence once shared a single coordinate in space, entanglement suggests that expansion never truly severed those original ties. We live in a universe defined by a hidden, persistent architecture of connection.